Hi everyone, thank you for taking my talk on ConstraintProgrammingExtensions.jl, which is a Julia package that provides an MY extension for constraint programming. More precisely, it's about bringing constraint programming to Java. So first of all, what is constraint programming? It's a way of formulating combinatorial problems. That's really focusing on the combinatorial side of problems. So with constraint programming, it can't really work with continuous problems with some exceptions. The initial focus of constraint programming was on feasibility, but nowadays optimization is also possible for most solvers. Constraint programming is quite different from mathematical optimization. For example, you have no duality, you have no convexity, no linear or continuous relaxation, you have no differentiability. Really, you're focusing on the discrete aspects of your problem, and everything that reminds you of continuity is removed. On the other hand, what you have is just not a set of equations and inequalities as constraints, but you have much more generic sets, and I will speak about them later. If you compare, in mathematical optimization, the support that you have for combinatorial problems is more an afterthought. It's adding a few variables that you constrain to be integers instead of having really discrete structure in the whole modeling infrastructure. Constraint programming has had quite a few successes in operational research in general, mostly in domains around scheduling, such as timetabling or resource allocation. For example, you can use constraint programming to have a really intuitive model of Sudokus, which is a kind of puzzle that some people really like. So here is an example of a Sudoku puzzle. You have a grid of 9 by 9 cells, and in each cell, you want to put a number between 1 and 9. Some of these numbers are already given, and you want to fill this cell respecting some constraints. Each digit can appear only once in each row, in each column, and in each block, where the blocks are highlighted in black. So that's it for your constraint programming models. You have as variables the digit for each cell, which is just a number between 1 and 9. As constraints, you have no digits, all the hints that you have. Then you have for each row a constraint that each digit must be different from the other digits in the same row. And that is already one kind of constraint that you can have in constraint programming. It's not something that's really natural for mathematical optimization. You have the same kind of constraints for each column and each block. And that's really it for a constraint programming model. Think of it if you had to do it in MIP. That would be much more difficult than this kind of model. And that's really where constraint programming shines. And now let's go on with ConstraintProgrammingExtensions.jl. My talk is divided in mostly 5 parts. First, I will describe the state of constraint programming in Julia. Then I really dive into the package I'm presenting and see in what state it is right now and what comes next in its development. Then I will explain what's currently missing in terms of features in Julia, MOI, and Jump to bring constraint programming really to its best. And also, finally, I will see what's enabled with this package outside constraint programming. But first, what's the state of constraint programming in Julia? Because usually when you're doing constraint programming, you're using different languages, such as usually Java. But you have quite a few CP solvers that are purely written in Julia. For example, Constraint Solver and CPO are 2 different solvers purely written in Julia. You also have the CBLS interface for the Julia constraint organization. All of these 3 pieces of software are based on MOI, just like Jump. There's also another CP solver that I'm aware of, which is Interval ConstraintProgramming.jl, which is based on Modeling Toolkit, which is a completely different modeling environment than Jump and MOI. And apart from those solvers, as far as I know, there's just one external CP solver that's not written in Julia, and this one is wrapped in Julia using the package I will be presenting today. The main problem I see with this quite large number of solvers in Julia is that there's no easy way to write a model for several software packages at once. You have to write models that are slightly different for each of the solvers. It's like you would have to write a completely different model for Cplex or for Gurobi. That does not really make sense because they're implementing exactly the same features. So that's really the major goal of constraint programming extensions. It's really to sit at the same level as MOI to provide an abstraction of solvers that other people can use, mostly modeling layers. It's really working with MOI as it's an extension of it. It's not a completely new infrastructure. It builds upon what already provides. The major goal of constraint programming extensions is really to bring expressive power of constraint programming to both MOI and Jump. So more precisely, that means that I would like this system to be approximately on parity with MiniZinc, which is a similar modeling platform for constraint programming. That means that in the end, it should wrap most of the constraints that are provided in some well-known CP solvers, such as Cplex, G-code, Jacob, and so on. There are also non-goals for this project to avoid giving it a too large scope. For example, I don't want to give directly access to the whole set of features that's provided by CP solvers. For example, callbacks at some point when in the exploration, or more specific exploration tuning, providing new kinds of constraints via new propagators. These are not things I'm interested in right now. Also, I don't want this project to provide in the short term pre-processing of your formulation to improve it or to reformulate it in non-naive ways. I want it to keep quite simple, just to have a goal that's achievable in a reasonable amount of time. This idea of providing a common interface to several CP solvers is not exactly new. And the main competitor I see to this project is MiniZinc, which I talked about earlier. MiniZinc is really a dedicated language to describe CP and MIPS models. You can also use it to describe SAT models, for example. There's a variety of MiniZinc that's called FlatZinc, which contains only the bare minimum number of constraints. For example, we have no greater than, we have less than constraints. And this sub-language, so to speak, is used to communicate with solvers so that they don't have to pass a much more complex language for users to input their models. And MiniZinc is mostly a compiler from the MiniZinc language, which is quite high level, to FlatZinc, which is a lot more low level. And to do so, MiniZinc uses the notion of bridges. It's not called in the same way. Actually, it doesn't really have a name for MiniZinc, but it exactly as MOI bridges, which are a way of transforming a constraint into another set of constraints that's equivalent. With MiniZinc, each constraint has a default implementation in a new set of constraints in the hope that the solver behind it can support the new constraints. Otherwise, the solver has to redefine these basic constraints. So that's what you can do to use MiniZinc with MIP solvers. MOI bridges, on the other hand, work in a much more flexible way using graphs, so that you choose the bridges that you want to use, and you're sure that in the end, you will end with constraints that are supported by solvers. MiniZinc also comes with a complete idea, with a tree visualizer, config debugger, and so on. So it's quite a full-fledged tool. On the other hand, you have NumberJack, which is a Python library to model the same kind of models. And here you have a Python library instead of a dedicated language. NumberJack can import MiniZinc models as Python files. So you input a MiniZinc model and you create a new Python file. NumberJack can also import and export models as XCSP files. There's also the notion of decomposing a constraint into simpler constraints so that you can map onto solvers easily. So that's the same notion as in MOI on MiniZinc. And similar to MiniZinc, you have no flexibility in the way that models are transformed. Survivor, which again is a dedicated language to describe CP, SAT, or SMT models. And it can reformulate models to improve the solving times. For example, it does quite a lot of work to remove any symmetry that you could have in your formulation. More precisely, the specific point of Survivor is that it can cast your CP or SAT models into SMT models, which are mostly used for theorem proving. This really enlarges the number of available solvers for your model. OPL is the only commercial software I'm presenting here, and it's released as part of the Cplex optimization studio. which is an IDE for Cplex, both for mathematical optimization and constraint programming. OPL does not provide any kind of reformulation. So if you write your CP model, it cannot be solved using the MIP Cplex solver. But that's it for the competition. What is the current state of the package I'm presenting today? There are quite a few standard CP constraints and functions that are already available, such as computing in absolute values, having constraints such as all different, used for the Sudoku, finding the minimum and the maximum in an array. You can have higher level constraints such as bin packing on knapsacks, conjunction, disjunction, or even reification of other constraints. So you can do quite a lot of things just for the modeling part. For example, if you want to use the new functionalities to write the Sudoku model, here is what you can do at the MOI level. So you first create an integer variable for each cell in your Sudoku grid. Then you add an all different constraint for each row, each column, and so on. So it's really a syntax that's hugely similar to what you can already do in MOI for linear models. The point of having that many constraints is not really to have models that are easier to write for the users. It's also so that your models are easier to solve for the solver, because CP solvers really have a huge number of so-called constraint propagators that are used to deal with specific kinds of constraints. So if you give the information about one specific constraint to your solver, it can work very efficiently. Whereas if you only decompose the constraints as linear constraints, you cannot use the same kind of propagators, and the solver will not be as efficient. For now, there's only one solver accessible through constraint programming extensions, which is Cplex. Reason why writing new solver wrappers is quite hard is because usually you don't have a low-level API for CP solvers. If you take Cplex or Groby, for example, you have a really low-level callable C API with a very small number of functions to map. But for CP solvers, what you usually have is only a modeling API, which is really high level. And you have to do quite a lot of calls to perform the same kind of operations. You have to build expressions before constraints, for example. Also, many CP solvers are written in Java or languages that only run on the JVM. So that creates quite a bit of a burden to wrap those solvers to Julia. Also, another difference in CP solvers with respect to method solvers is about the file formats that you can use to share models between solvers. For linear models, what you can use is an LP or an MPS file, and that's something that you can use with almost all solvers. That's not true for CP solvers. There are quite a few languages that you can use to describe your models, and you can move from one environment to the other, but there's no format that's as ubiquitous as LP or MPS. So you have MiniZinc, for example, as a way to share models. You also have XCSP, which is an XML variant. Ample also can do some CP models. Dymax is a version that's only works for SAT models. So these four are quite high level. You can use a lot of different constraints. You also have FlatZinc, which is a variant of MiniZinc, and it only focuses on low level constraints. So to provide models to a lot of solvers from this Julia package, I implemented an import and export module for FlatZinc, so that it's possible to move your models to other environments. Also, there's a quite common problem with CP solvers is that not all solvers implement the same kinds of constraints. And it's exactly the same problem as in MOI, where the user doesn't always specify the constraint in the way that the solver would prefer to have this constraint. So it's the same solution. Use bridges, a quite flexible way to reformulate a problem. For CP, it's better to write two kinds of bridges. First, between high-level CP sets, because some sets are just a variant of another. For example, for bin packing, you can add some weights, and that makes a new set. So you can make a bridge between two kinds of knapsacks. But you can also implement bridges between CP sets and MIP models. so that you can really enlarge the number of possible solvers for your model. So far, in constraint programming extensions, there are 50 constraint bridges, which is roughly 6,000 lines of code, excluding tests. When you compare it to MY, it only has 23 constraint bridges, and it's really enough. It's only 5,500 lines of code with a lot of general infrastructure that can be reused everywhere. But with the 50 bridges of constraint programming extensions, I'm far from done writing bridges, because there are a lot of sets that could be useful for other solvers. There's also something specific when writing those bridges, is that you may need some information about the function that you're dealing with. So for example, you might want to ensure that some variable is binary when you reify some constraint, or to get the upper or lower bound on an affine expression to get an estimation of your big M. So I wrote some kinds of traits, which are a way to get information about functions, and you can use it to perform more dispatch to get the most specific function to call in some cases. And then what comes next for constraint programming extensions? In the short terms, I will implement quite a few more bridges to provide new functionalities, such as new sets that you can use in solvers. And MiniZinc provides a quite interesting list of sets that are useful to implement. It also provides sample bridges for these problems. Also, I plan to flesh out a bit the implementation of CP functions so that you can use other kinds of models for your application. In the medium term, it will be better to have a lot more solver wrappers available so that you have more flexibility in the way you solve your problems. And that also involves using this package for Julia CP solvers. In the long term, it would be useful to bring more redundant bridges so that you have more, for example, MIP formulations, so that if you have a solver that proposes SOS1 sets, you don't have to rely on big M constraints to get better performance. It will also be best to be able to model SAT models, but also to have Boolean algebra as constraints natively. In the very long term, that means after the first mature versions, I would like to wrap more features from CP solvers, such as how to guide the exploration, adding callbacks, or adding new constraint propagators. But that's really for after, once the basics are done. But to get to this point, there are quite a few things that need to be dealt with in the JUMP ecosystem. That includes Julia and MY. First, let's talk about nonlinearity in MY and JUMP. So MY is really a huge rewrite of JUMP for the previous versions. However, the NLP support there is not really rewritten with the new ideas. So it doesn't always play well with all the concepts in MY. There's a complete rewrite that's currently planned, but as far as I know, no one really knows exactly how the rewrite will be done. CP solvers really require some kind of nonlinearity because they may have some specific machinery for constraining, like counting the number of 4s in an array and ensuring that this number is at least some lower bound, such as 4. But how could you represent this within the MOI framework? You could say that the count, the number of 4s in the array, is a nonlinear function, which you constrain to be in some standard set. There's a quite huge difference with other NLP needs, because you don't have automatic differentiations for CP solvers. You don't need to compute gradients in this case. So I'm planning to introduce a lot of new function types that are based on MY types, and to use it as a prototype for maybe the next generation NLP support in MY. So that means to have objects to represent an affine combination of nonlinear functions, but also products of nonlinear functions that could be used to represent geometric programming and polynomials. Then a large number of more complex functions, such as an exponential, a logarithm, and so on. On top of that, there must be a lot of CP-specific functions, such as counting elements in an array or indexing an array. This way of writing the nonlinear functions is really usually similar to a MATLAB format, which is a novel representation of optimization programs in JSON. And that's really driven by the same principles as MY. On the solver side, this implementation could be really useful because you could directly see if some combination of function is natively supported. Otherwise, you could use existing function bridges to decompose your constraint into several other constraints. A huge pain point when implementing constraint programming extensions was variadic parametric types. So that's something that really happens with conjunctions and disjunctions. For example, a disjunction is an OR that you apply between several constraints. For example, you want that either x is greater than 0, or y is greater than 0, or z is greater than 0. And for this, you need a disjunction with 3 arguments, which are the 3 sets that you're using. The problem in this case is that you have a lot of variety that's possible in the number of sets and in the types of the sets. So that's why you need variadic parametric types, and that's only possible in Julia with tuples. So I have to parameterize the disjunction with a tuple of types, and that gives, for example, this disjunction with an n tuple. And that's where the problem begins, because when you want to dispatch on this kind of thing, you have to write one function per number of arguments and per type of arguments. So that creates a lot of code bloats. Or you can also rely on introspection to write much more complex code to deal with this flexibility. So that's one point when I think that the design should be improved or the language be improved. The third missing point in the JUMP ecosystem is, in my opinion, structured variables. Usually in your optimization solver, you only deal with floats and integers. And then someday you think that you should deal with complex numbers. So it's still a number, but it's also a pair of floats. And then you go to CP solvers. And then you can need, for example, time intervals, which is also a pair of numbers, a beginning and an end of an interval. You can also have graphs, which is a large number of binary variables. And for this, it would be best to have one variable index that's available for each kind of new variable, while still having the possibility to access sub-variables if you need to. This is just not for modeling ease, because sometimes the CP solvers have graphs as variables. It's something that they natively support. It would be best that the user can access these. So currently, Complex Opt interface implements a solution that is roughly do nothing. You do nothing when you create variables, and you have to use them in a quite specific way to ensure that you retain this complex type of the variable. If you use a constraint such as a single variable in equal to, then you can lose this complex property. Another solution would be to create new kinds of variable indices that could be composed of several variable indices. And MOI at variable function would take as a new argument the type of complex variable that you are creating. And this type would also be reflected in the type of the affine functions, for example, that you could be creating based on these variables. And then once all of this is developed, where can we go? Because most CP sets already have MIP bridges, and the number of CP sets that can be bridged will only increase. So that means that modeling becomes much easier for users. For example, you can use bin packing, for example, or circuit constraints just in one line instead of adding a large number of linear constraints. Probably right now it's not the best model you can think of, but at least for the user, it's easier to think of a first model and This new nonlinear infrastructure can also be built upon to, for example, implement the discipline convex programming paradigm, which is a way to convert generic convex expressions into conic constraints. However, with this current infrastructure, I make absolutely no claim about the performance or the compatibility with automatic differentiation, because I have no real need for these 2 points. And then what can you do to help this go on? For example, you can spread the word for Julia and constraint programming, because for most people, what you have to do is to use FlatZinc or Java, but you can still do constraint programming in a nice way in Julia. And people really need to be aware of this. I would also really appreciate to discuss the implementation to see if there are things that can be done in a better way. And then to write new solver wrappers to check if all the needed features are already available in the package and what new sets, for example, must be added. Benchmarking could really be important to, for example, compare this package to FlatZinc when it's lowering models to FlatZinc, but also to compare to the NLP code in JUMP to see if this nonlinear prototype could be worth. Also, the documentation is not exactly well written right now. It's just reference for existing sets. There are no examples for users, for example, or documentation how to wrap a new solver. So these things would be really helpful in the documentation. So that's all for me. Thanks for your attention.